As I said, even though this is a least efficient reactions, still you should prepare, question like this because that's easy to write. And then this, at least the concept goes the same. The hydration reaction in water. So the proton is the one that gets by the pi electrons, right? Proton is going to be H double bonds. So you got to worry about which carbon is going to be the proton, and then you should consider yourself the task is producing the more stable intermediate. So the carbocation go to the benzylic position is way better than the other one. So you're going to hydrogen go to this carbon, less substituted carbon. Carbocation go to the more substituted carbon. Not only that, that's a resonance stabilized by the benzene. So this is really way better position. And then water capture the carbocation, and then proton lost in the end. So you get alcohol like this. So this is a pretty simple reaction, this question. This is a very simple. So if we're going to ask questions like this and on this subject, we wouldn't ask this question. If you get this question like this, then you should feel yourself really lucky. I will ask this question. In the end, what I did looks really similar. You get that there, you get this one there. I only added the one carbon in between. That's the only thing I did. I only did that. So if you kind of don't understand, but you solve so many questions, you might have memorized how to solve this question. Now let me show you what you probably would answer. You see this question answer, proton is given to double bond, more substitute to the side, less substitute to the side, proton go to less substitute to the side, so more substitute side get the carbocation, attacked by the water, so OH sitting on the more substitute side. Yeah, you can patternize that. I'm not saying that that is not useful. Sometimes maybe that works. So let's do the same thing to this. You got double bonds. You proton go to less substituted side. You get the more substituted carbocation right there. And then water captures it. So OH is in there. So I did exactly the same thing what I did over here. If you're parallelizing it, you can answer that. And then I'm going to say, no, that's not the right answer. I'm pretty sure that's the where you get lost many times. You don't see the differences between those two because you don't try to understand the mechanism. So that's why the mechanism is that we teach first. I know you try to take a shortcut to answer the question, so you memorize, oh, I do this, I do that, and then we answer. And then we don't ask those questions in the test. You probably see that already. When we ask a question, we make the question like that so you can actually fall into trap. So if you don't study, you will pay for it. And you may have an easier time to going to the movie or taking a party, having fun with friends, but you will suffer with grade layers if you do that. I think you are here to many reasons. Having fun is one thing, but also you want to educate yourself to prepare yourself for your career. So I hope you make the right choices. I cannot twist your arm. You are adult. You know what to do. So let me tell you why this thing doesn't go the same way. The answer is this is a carbocation. What did I tell you when you see the carbocation first? You have to think about the possibility of rearrangement. That's a tertiary carbocation, which is not bad. I'm not saying that that's a bad carbocation, but this is next to the hydrogen, and this is next to the benzene. If this hydrogen move over there, you're going to make a carbocation. It's a secondary carbocation, but it's a resonance stabilized carbocation. Benzylic carbocation. That's way more stable. So this rearrangement happen almost automatically, and this will capture the water, and then OH goes in. You may get a little bit of that. That's going to be the minor product. So I'm not saying that you get 0 point. Maybe you get partial credit. But The main major product is this. So that's what I said. You dump acidic water to double bonds. Maybe easy to make the hydration to double bonds, but because of carbocation reactions, there's a possibility of a rearrangement. Anytime you see carbocation, you got to worry about the rearrangement. So this is the thing. We teach this, we ask that in the test. And then we also told you the carbocation rearrange multiple times. We give the pieces, you have to put it together. So that's what you need to study, you need to solve a lot of problems like this. If you fail that, you gotta understand why you failed in producing the right answers. Once you understand, then go prepare for this. It takes time. So do not try to find a shortcut. You really have to sweat on it. And there are tons of things like this. Maybe I'm warning you too much, but if you do it, it's going to repeat. So it wouldn't take too many times, but at least it's a doable. You got a lot of previous students, they all go through this, they got the good grades in the end, went to the medical school, whatever. The thing is, why this has to be something you have to take it because of go to medical school, I don't know. So don't blame like that. I have an easier life if they drop the MCAT drop it organic chemistry part. The thing is, if you have to choose a doctor when you are sick, would you go to a doctor who failed an organic chemistry? I'm pretty sure that would be different story, right? So anyway, I'm not saying that it's needed, but it's like a math. How many times actually you are using calculus for the daily life? Well, then why are you studying for it? Right? Because it teaches you the logic. These things are logic of the life science. Many things happen this way in the micro scale. So that's what we learn. And then anyway, this is the example I want to show you that, you really have to understand the holistic view, not just, patronizing the proper sodium. Something that works. I mean, many times it could work too. You get many questions answered right that way, but there are some questions you will miss. Then you really have to go through that and understand why you missed those things. Because that will teach you what you need to understand properly at the beginning. All right, the second part, this part is pretty simple. As I said, reagents are telling us what it is. This is the mercury acetate, sodium borohydride, two sequential reactions. That's oxymercuration, demercuration. So once you recognize this is a reagent oxymercuration, demercuration, then probably you should remember what's the mechanisms and then follow through. So mercury acetate breaks it down to mercurium ion. That is going to be attacked by the pi electrons. So you get the mercurium ion sitting on the carbon like this. This is the part that sometimes the water, we don't even say that because water is always everywhere on Earth. Believe me, it's really difficult to not having even residual water in anywhere. Water is everywhere. So that's even small amount of water is good enough to make the reaction go, unless you are adding other reagents there. So the mercury will pull into density from the carbon it bound to, but the more substituted carbon lose more. That's the concept I've been repeating so many times. Believe me, this is not the last time we're going to talk about. This thing is going to keep appearing again, even in OK2. So I really hope that you understand this concept. Water makes an attack on the backside. So hydroxyl groups on the more substituted carbon, mercury goes to less substituted carbon. They are opposite to each other, they're trends. And then mercury replaced by the hydrogen in the second step, sodium borohydride, that will be adding this. That's basically what it is, but the thing is the hydrogen, we don't normally show, so this is actually done. So, but you can show this if you want to emphasize hydrogen added there, so that's really good. The point is, this is a Markov nickel products. I mean, you may be able to do this like that, follow the mechanisms. But the thing is, that's not the only question you should prepare yourself for. You should prepare for something like this too. Let's say you have to make these things. You got double bonds here, double is gone. So we added to double bonds. So this is the electrophilic addition reactions. Once been added, you got methoxy groups added there. So first question is, you are adding alcohol here because the H was added on this side, methoxy on the other side, put it together, we add a methanol, double bonds. So you know what's been added. Two, what you need to worry about is this a Markov-Nichols products or anti-Markov-Nichols products? Because there are different ways of doing things. So that's the reason I keep telling you how to differentiate those things, looking at where the nucleophile is sitting on. Hydrogen and methoxy groups, I would say methoxy is a nucleophile, and the methoxy groups are sitting on more substituted carbon compared to that one, right? I'm not comparing this one because this one doesn't have a double bond there. These two are making double bonds. These are more substituted side. That's less substituted side. More substituted side gets a methoxy group there. It's a nucleophile. So nucleophile sitting on the more substituted side. So this is a Markov-Nichols products, right? So now, once you figure that out, then the stereochemistry we need to worry about, but this is an open chain structure. The stereochemistry doesn't really apply here. So these are Markov-Nichols products. Then you got to think about your databases. Do I know any reaction that add an alcohol and make some Markov-Nichols products? Then of course you do. We just talked about it. Alkoxy mercury equation. If you remember that, it will make things easier. If you don't remember that, are you in trouble? Well, maybe a little bit. But there are other ways to handle these things. I'm going to tell you that. First thing is, alkoxy mercuration demercuration is a variation of the oxymercury demercuration. Everything same, except the reactions that take place in alcohol as a solvent, not water. So the mercury acetate will make a mercurium ion, add it to double bond the same way. I mean, there's no stereochemistry needed for the because open chain structures, but for the argument's sake, I just put it like that. More substituted carbon will be more carbon-cation characters because the neighboring groups can donate in density. That's the what nucleophile. This time is not the water, it's an alcohol, it's an attack, and losing proton in the end. So you get the methoxy sitting on the more substituted carbon like this. Mercury is still there, but we have to get rid of mercury. So that's second step, the demercuration step. Sodium borohydride is added to replace the mercury with the hydrogen. So that is basically the simplest answer. But you got to remember, there are alkoxy mercuration, demercurations. So that's the reason, if you make a study card, that will help you memory. Whoever said that organic chemistry is nothing to memorize is a BS. Believe me, it has tons of things to memorize. But there's a huge amount of memorization, or little bit of memorization, it makes a difference. If you try to memorize everything, it almost becomes an impossible task. If you try to reason it out, you make the memorization a little bit smaller, it helps. So that's the reason why we study mechanism. Studying mechanism is not preventing the memorization at all. I mean, maybe some genius can handle it that way. But most of the people, like including me, I have to memorize a lot of things. Especially organic chemistry, it's been developed so many years. People didn't really care about the mechanism all day. They just found out if you mix these two, this apple. If you mix that two, that apple. And that becomes a really useful, trade secrets of people keep developing them, and then you need to memorize them, unfortunately. Sometimes not everything's explainable in the universe. Surprisingly, even after so many years we try to study for it, it just sometimes we cannot do anything about it. So anyway, so this is a kind of oxymercury demercuration. But as I said, what if you choose a wrong reagent? Let's say you do the hydroboration to that. If you do the hydroboration to this, hydroboration works different way. It adds H and H2 at the same time, and hydrogen on the more substituted side, H2 goes to the less substituted side. It's because of static reason. So you're going to add a boron, end up being on less substituted side. That will go to the second step, oxidation step, and then you get the OH sitting on the less substituted carbon. That's an anti-Markov-Nichols product. You can see that monochemical products and non-monochemical products, something that you really have to keep analyzing the product if you have to find out what reagent you're going to use for. Obviously, this is an OH, not a toxic, so you're going to do something else afterwards. Let me say that our toxic molecular creation is nice things to remember, but sometimes we cannot have an infinite amount of memorization capacity, so you forgot about that. Would it be the real disaster? I would say no, because let's say you forgot about the oximer curation, but somehow, at least you should remember the oximer curation, right? Because this is one of out of two. So you do the oximer curation, which means that you do the same thing, mercury acetate, not in alcohol, but in water. It's going to make the same intermediate, just like we made it here, and then it's going to be attacked by water. So OH is going to sit on there. And then you treat them with sodium borohydride, mercury, get rid of it with the hydrogen, you get this. This is not that, right? So, will that be a completely wrong answer? No, I said, at least it's partially correct. You got the OH to the right side. I can recognize that. So that will deserve the partial credit. But I hope that you can do further because you can make this from that. Actually, that's a question in the test too, remember that. How you do that? You take this hydrogen away by strong base. You can treat the sodium metal with sodium hydride. That way you can make an alkoxide, oxygen anion. Now you need to react with an alkyl halide. So methyl bromide, it makes an attack SN2, fix it out, so you can make this. So there's a way to make it happen. And then if you do this way, long around, will I take some points away? No, this is also another good answer. So I will give a full credit for this.